Hey everybody, Thursday. Welcome to Thursday. Today it's not a review day, it's a put it all together day. We're going to take Monday's calculation of energy and light, Tuesday and Wednesday's lab about the idea that a photon gets emitted as electrons change levels. And we're going to put it all together and look at the emission spectrum of elements. That different atoms emit different emission spectrums. And so we're just going to kind of do some math, kind of apply the concepts, and create this idea of an emission spectrum, where we're going to create this spectrum from 400 nanometers, or violet, to red, that shows particular colors of light produced by certain elements. So I'm going to do a quick review. This should help you with the homework that's due. Let's make it due Friday. I'm going to do two things. I'm going to make Friday, it's going to be due Friday, one. Two, though, I'm also going to have something else Friday. I'm going to have a cosmos for you. You know what? It deals with this stuff. It deals with light and stars and space and stuff, which will lead into what we do on Monday. And there'll be a little cosmos quiz. You all know how to do it. And so that'll be Friday. But the homework also won't be due until Friday as well. So there'll be two things due Friday, but you got today. You should be able to finish it. But if you need, ask me questions or something like that, maybe I'll hop on Meet and help out people, as well as a Cosmos video Friday. Good? Cool. Let's talk about it. All right. So the homework consists of effectively like three different things. And that's what I'm just thinking in my head. Maybe it's four. Three different things. The first is energy of different light waves. So let's just jump right into it. Here I've got four energy levels. I've got the ground state energy level, N1, N2, N3, and N4. These are the places that excited electrons can be. Then I've got an energy value for each one. So the bottom energy is -6 electron volts, -4 electron volts at 2, -2 electron volts, and -1 electron volts up at 4. So if I've got an electron at the ground state, nothing's happening. Boom, excite that electron. So now I've got an electron up here at the fourth energy level. Well, it can now drop, but it can drop in a ton of different combinations, and you need to know all the different combinations. And it's not hard, you just got to put them together. So let's start. And it's easier to do it by a pattern. So if it's in 4, it could drop to one of three levels. It could drop from 4 to 3, and that would emit a photon. It could drop from 4 to 2, and that would emit a photon. It could drop from 4, and I'm going to stop drawing photons. It could drop from 4 all the way down to 1. It could do one big drop, and that would emit a photon, probably an ultraviolet, high energy, big drop, -1 all the way down to -6 drop. So that would emit a photon. But what about this first one? Once it drops down to 3, well, it could drop again. It could drop from 3 to 2. Or maybe it just drops all the way down to 1. And back here to this, though, back here to the one that's at 2, that dropped from 1 and then down to 2, or the one that dropped from 4 to 2, that one could drop down to 1 again. So I've got a total, if I have 4 energy levels, I've got a total of 1, 2, 3, 4, 5, 6 different drops that I could look at. So for this particular one, let's just label them A, B, C, D, E, and F. All right, all the way across. Now, a couple things I could ask you to do with these. First is determine the energy of each drop. Well, with this, since I've given you the energies, the drop from 4 to 3 is equal to 1 electron volt. The drop from 4 to 2, from 4 to 2 would be equal to 1 to 4 would be 3 electron volts. Everybody see what I'm doing there? So if I want to know the different energy drops that exist there, I can do that. What about from 3 down to 2? 3 to 2 is 2 electron volts. The thing I want to call your attention to here is that the drop from 4 to 3 plus the drop from 3 to 2, so 4 to 3, 3 to 2, 1 and 2, adds up to the total between them, 3. Good? It's like stacking. 1 plus 2 equals 3. Right? Add them together. So That's it right there. What about if I didn't know these energies, though? How could I calculate that? Well, remember, you've got an equation. The energy of a photon is equal to hc divided by the wavelength. So if you know the wavelength of light, if you know the wavelength, you can figure out the electron volt when hc is equal to 1240. 1240. And that's on the top of your homework there. So AB, use this equation, calculate it. C, it's not AB, 1, 2. Question 1, 2, use this equation. Question 3 on the homework. Question 3, you're going to take 1 and 2. You'll have calculated the energy drops for 2 of them. Just add them together. Boom. I'm telling you how to do the homework right here. Hopefully you watch the video. And then we get to number 4. Number 4 says calculate the wavelength. Well, how do we calculate the wavelength? Well, if you just figured out the energy, to figure out the wavelength, I just solve for wavelength, energy. Remember, I swapped the 2, solve for the unknown. So hc 1240 divided by the energy from number 3 will give me the wavelength for 4. Okay. Anyway, we then get to this idea that each of these different drops can produce a wavelength. They're different wavelengths. You got to figure out what they are, what their wavelength is, and we can plot those different wavelengths. When you plot them, you actually create what the energy spectrum, this emission spectrum, would look like. So this particular one, I don't know, maybe this big drop here, we'll just say C produces light. So let's say C is about 450. Oh no, that'd be this one. Yeah, C is 450. B. So we could plot, we come down here and we would plot a line. I would plot a vertical line at the 450 point on the spectrum. All right, so I'll plot a line right there. And that color would correspond to whatever wavelength that is. This particular one might be violet. All right, let's say one of the other ones produces a wavelength of 550. Well, I'd put that there. That would be green. Reference my chart from the previous day. And then maybe the really small drop here, A, not very much energy. That's going to give me one that's red. All right, so I have now plotted A, B, and C right there with their wavelengths using the numbers that I calculated. All right, that was all of the first question there. Model 2 actually gives you this and asks you just to match up some wavelengths. Do your best on that one there. And then Model 3 gives you the drops, actually tells you the energy drops, so it's much like this setup. You figure out the different drops, the different changes of energy, and then just plot them. Not too much calculation, just some addition and subtraction. Do your best on this. I'll come back on tomorrow when I introduce the Cosmos video. I'll give some more feedback based on how people are doing and what questions people are asking. All right, so we're going to start out with a demo of just a white light. This is a black body. Black body just means hot object. Hot objects make light. I mean, this is really hot objects make light. The hotter they are, the bluer they are, the cooler they are, the redder they are, and it kind of shifts back and forth. But hot objects, like incandescent light bulbs, make white light, and they radiate with all the colors. So I'm going to put this plastic color over, or the clear plastic sheet over the light bulb in front of the camera here, and it's called a diffraction grating, and it's gonna spread out the light, and so it shows you all the colors that are making up this white that we see. So why do our eyes see white? Well, because we're seeing all the colors. So check it out. We're gonna take this diffraction grating and place it over the light bulb, and there you go. When you do, you have the white light here, making it that color, and then you can see the spectrum. It's creating from the middle. It's creating the spectrum on either side. You've got violet all the way to red, and it does it on both sides. And there'll be some ultraviolet here, infrared here, but you can see the entire spectrum because all the colors of light are being produced. So now we're going to replace that white bulb with a tube full of mercury. Now that's mercury vapor, so it creates its own color. You can see this glass tube here.
that's filled with mercury. I'll put a voltage across it, and it sends electricity, which effectively energizes those atoms and causes the electrons to jump up to a higher energy state and then drop down and produce the colors that they do. All right, so we turn it on, and you got a blue light. It's like a cyan blue. It's definitely not blue. Definitely cyan light. Now, is it really cyan? No, it's made up of a bunch of different colors. So we can put that diffraction grating down in front of it. We'll do that in just a second. First off, just notice the color. The color is like the same mercury vapor lights that you would see wherever. I mean, it's what mercury vapor lights are. They produce this bluish color. Now we put the diffraction grating in front of it, and you can see that the cyan color that we're creating, that the light is actually a blue and a green, and then another light green here. So this is actually splitting apart the light that you're actually seeing from one spot into the colors that are making it up. Now, let's back it up just a little bit. So these are the actual energy, like the electrons dropping from one energy level down to another. And if we shift over and look at mercury, or any element really, we can see the different colors that they produce. So if I click on mercury, which we were just looking at, mercury kind of produces these different yellows and blues and greens, and they come together to produce that kind of cyan color that you see. Now there's some very light reds and others, but the really bright ones are the blue and that. So these lines are what you guys are producing in these calculations that you're doing on the sheet when you plot the different things. The element that has mercury in it will have all of these different colors. Now, if instead I looked at neon, we click on the element neon, then we see it looks like a whole bunch of colors that come out of a neon light, but the predominant is all these yellows and oranges in here. Yeah, there's a little bit of cyan and other lines here. I mean, we have probably 30 different lines for all the different electron drops within the atom that produce the different photons as they come out. Now, but the neon spectrum is dominated by these yellow to red and orange in the middle, and so that neon glow that you see from a neon sign is going to be very orange. So let's take a look at that on the demo. So here's neon. It's a very orange glow. In the middle there, when you split out its spectrums, you can see the green and the violet a little bit, but it's really dominated by this orange to red glow. This is a neon glow that you will see as we split apart that light that's making up that center glow there. So again, you got these colors here, but dominated by the oranges to red. So next we're going to look at hydrogen. Let's jump over. Actually, start here. Well, hydrogen here. Got a hydrogen lamp. Nice little kind of purplish glow. So sure enough, boom, magenta looking glow, but made up of a blue, cyan, and red. Now these are the ones we've been doing all the calculations with. So there's also a violet ever so slightly in here. So you've got a violet, a blue, cyan, and red. Those four colors that are the four wavelengths that get created by a hydrogen color. So when you excite hydrogen atoms and allow them to electrons to drop, you produce this different color here. So if we grab hydrogen, boom, hydrogen, we see that blue, the cyan, and the red that would emit if we excited the hydrogen. There's a little bit of violet there as well. We can jump over, see helium. Helium's going to have some others. And then again, when you look at the actual color of the thing, they all come together and produce whatever color you see as a thing. But then we split them out and we see the different light that makes it up. And this is actually how we identify what stars are made of, which will be the topic of Monday's assignment, but also the cosmos for Friday.